So in this video, we are going to learn about rate laws and reaction order. So rate laws, I want to explain how they're different from the rate expressions that we were discussing earlier. Rate expressions, you can write a rate expression for every single thing in the reaction. So you can write it for a reactant, for a product, for the reactant in terms of how it's being consumed, for the product in terms of how fast it's being formed. Now, rate laws have to do with the overall reaction. So you actually don't even look at products in rate laws. So the rate law is the mathematical relationship between the rate of the reaction and the concentrations of reactants and any catalysts you may have present. So notice how it didn't mention products. And it's directly proportional to the concentration of each reactant raised to a power. Now this power is a very special number, and it has a name. Now, we actually call these the order of each reactant. So these powers right here are the order of each reactant, okay? Now, we also have something called K. K is the rate constant, and it's independent of the concentration. This is determined experimentally, and it's right there. You multiply it against your concentrations raised to the powers. And then your overall order of the reaction is whenever you add up both M and N. In other words, the powers that you raise the concentrations of the reactants. Now, something I want to point out is, we put these numbers in front just to show how this is what we raise our concentrations to. But in the next slide, I discuss how it's not necessarily related to stoichiometry. So again, just to summarize what reaction order is, the exponent is what gives you the order. The sum of the exponents gives you the overall order of the reaction. And here, to show you an example, we have the reaction is second order with respect to NO. So NO is second order. First order is with respect to O2. So O2 is first order. Overall, that M plus N, which is, 2 plus 1, for example, is 3. So overall, the reaction is third order. And this is what I was alluding to. So order does not equal stoichiometry. The order of the reaction must be determined experimentally. It is not necessarily related to the balanced equation. So in the previous slide, I had the coefficient of NO highlighted in red, and also the exponent, and it looks like it may come from the same thing, but bear in mind they are not directly related, does not equal the same thing. So to show you some examples, here we have N2O5, the overall rate of N2O5 being consumed and converted into these products. Even though we have a coefficient, a stoichiometric coefficient of 2, that does not match the order of this N2O5 being consumed. And you can see the same thing for these other ones. So just some more examples. Here we have this CH3CN being converted into CH3NC, and we can see its rate law right here. Here we have H2 plus I2 being converted into HI. Here we have the rate law, and here we have a just very specific type of reaction. It's autocatalytic. You don't have to worry too much about that, but they can get a little bit more complicated, and they do include catalyst when necessary. So now we're going to practice writing a rate law when we are given reaction orders. So an experiment shows the reaction of nitrogen dioxide with carbon monoxide, and it shows that it's second order with respect to NO2, zero order in CO at 100 degrees. What is the rate law for the reaction? So we're going to start off with our basic rate law, which would be rate equals our K and then our reactants. Remember that we don't really care about our products when writing rate laws. So always our reactants. We know that we're going to have a M, you can call it whichever one you want, but in this case, let's call the the power for NO2M, and then for CO, it will be N. So we have our base, rate law. Now let's figure out what the orders are. So they told us that for NO2 it's second order. So what that means is that M equals 2, and for CO it told us that it's 0, so N equals 0. So let's go ahead and rewrite this. So rate equals K NO2 raised to the 2 and CO raised to 0. So we're pretty much done. This is technically the answer, but just to kind of help you understand why in future rate laws you may not see the component of something raised to a 0 as part of your equation, as part of your rate law, because anything raised to a 0 essentially is just equal to 1. So that's why we can omit it. So if you wanted to simplify this further, we could just write rate equals K NO2 and that. So this would also be correct for our final rate law. So in this next problem, we are determining order from a given rate law. So this reaction has this rate law. What are the orders with respect to each reactant? What is the overall order? So this is a simpler question, but definitely still a skill you need to learn. So the order with respect to NO tells us that it's 2 based off of that superscript, based off of that power, so second order. And then for H2, it doesn't have anything, written right there, so obviously that means 1, so first order. And then overall, you add these two. So overall order of the reaction is third. So how do we find the rate law? We have a method called the initial rate method. And first and foremost, this is something that has to be determined experimentally. It's not something you can just, somehow figure out or calculate it from something else. You need to determine this experimentally. So you need to do experiments, collect data, and then from there you can figure it out. So the rate law shows how the rate of the reaction depends on the concentration of reactants. And what we can do to figure the rate law out experimentally is that you can vary the initial concentration of a particular reactant while holding the initial concentration of the other reactant constant. So remember how in science, whenever you do experiments, you test one variable at a time, right? You're not going to sit here and change every single possible variable and then at the end be like, oh wait, what is exactly what changed the result? You can't do that. So in the same sense here, we are changing one reactant and then holding the other one constant so we can see a change in what it's related to. So we experimentally measure the initial rate of each with 2 different concentrations, and then the change in rate will be a direct result of the reactant that we changed, and then the order with respect to that reactant that we changed can be calculated. So you repeat this for all reactants. So in most cases you will just have 2 reactants, but you would repeat it with every single one depending on the reaction. So in this example, we'll directly be applying what we just learned. We're going to determine the rate law from initial rates. So here we have a reaction that has been studied in the lab, and they collected rate data. So for any of these types of problems where I have you calculate the rate law from initial rates, you'll have some sort of table, okay? So if you see a table, just know, okay, I'm going to need to calculate the rate law from initial rates, and this is, what I have to do step by step. So your first thing that you might want to set out, so your first step, is, maybe just write the rate law, right? You stick to the basics, stick to what you know already, and that is that the rate law would be the reactants multiplied by the constant. So again, ignore the products. So we have our 2 reactants, so NO Now I'm going to leave a space because I don't know the order just yet. And then we have O3. And remember, we can call them M and N. So our first job, or our job overall, is to find those orders. So we have the rate law, we have the skeleton of it, but we need to find M and N. Those are unknowns, okay? So first we're going to find M. So whenever you're looking for M, you need to look for the places in which the NO is changing, but O3 is changing constant. So remember, anytime you're trying to find a result directly correlated to a variable that you changed, you have to hold the other one constant. So for M, for the power that we're raising NO to, we need to look at where NO is changing, but O3 is staying constant. So we look at trial 1 versus trial 2. So you're always comparing 2, okay? So first, start off, with 1 and 2, easy. We look at 1 and 2. Is NO changing here? The answer is no. Next, we look at 2 and 3. Is NO changing the concentration? And again, it's no. Finally, we look between 3 and 4, and finally, NO is changing. Now, let's double check and look at what's going on with O3. O3 is not changing, so this is perfect. This is exactly what we want to do. So what you're going to do is you're going to divide both of these out, and you're going to divide both of these out, and you're going to compare them. So let's go ahead and do that. So I'm going to take all the information from trial 3 and 4. That's what we're focusing on, okay? You don't have to worry about O3 in this case. We're just looking at NO, right? We're trying to find M, which is related to NO. So let's first compare the concentration, and then we can compare the rate. So we are comparing trial 4, so T4 compared to 3. You always do the bigger one on top of the smaller one. So it would be 2 times 10 to the negative 6 molar, right? Mole per liter is also molar, so same thing. And when you divide this out, you see, times 10 to the 6 cancels out, so you end up getting 2. Let's look at what the rate compares to. So we're going to take, 4. And then the units are mole per liter times second. And then 1.98 times 10 to the negative 4 mole per liter times second. So when you divide this out, these are both 4. Sorry, they look kind of different. So that cancels out. And when you divide that out, you also get 2, right? This is about roughly equal to 4, roughly equal to 2. And when you divide it out, it actually does divide out, but you end up getting 2. So notice how you got 2. So as the concentration doubled, so did the reaction. So whenever you have a linear relationship like that, where if one doubles and the other one also doubles, you end up getting an order of 1. So now, because we know that these are directly related, directly proportional, the rate compared to the concentration, we would divide these out. So the rate divided, and I'm just writing rate so you can see where that number is coming from. Concentration, you end up getting 1. So overall, we found out that M equals 1. Okay, now I'm going to clean up a little bit here so we can work on the order for O3. So for O3, we would be doing the same thing. Now we are searching for N, and this is related to O3. So now let's take a look at our data. So in trial 1 and 2, we can see that NO is staying constant, so that's good, but O3 is changing. So let's go ahead and take a look at that. So when O3 for trial 2 versus trial 1. For trial 2 we have 6.00 times 10 to the negative 6 molar, and then for trial 1 we have 3.00 times 10 to the negative 6 molar. So, you know, right off the bat you can tell that that equals 2. So let's get that out the way. And then as far as the rates, we have setting that up wrong. We have 1.32 times 10 to the negative 4 divided by 6.60 times 10 to the negative 5. Now this one you might need to actually type it in your calculator because it doesn't seem so obvious. But whenever you divide this out, you should end up getting also 2. So again, we have the same situation where you divide both, right? The rates divided by the concentration, you end up getting 1. So here our N also equals 1. So we found the orders for both NO and also O3. So far this is what we know. We know that the rate law is equal to K NO, and you know we don't have to write a power to it because it's just 1, and then O3. So this is the answer for the rate law. Now there's another thing that we can determine from this data and information. We can determine, and this is our third step, we can determine K. Okay? So how would we do that? So whenever we solve any rate law, a general rate law, let's say A, you know, and B, just call it that. Let's say we wanted to solve for K. We would divide both sides by this. And then when we rearrange, you get K, sorry, that's ugly, K rearranging equals rate divided by the concentrations. So that's exactly what we can do here. We have enough information of everything in order to divide that out and get K. So let's say we're going to look at trial 1. And I know it's small, but I'll write it out. We're going to take the rate that we got, which is right there, 6.60 times 10 to the negative 6. And then we're going to divide by the concentrations of both reactants. So for A, or in other words for NO, 1.0 times 10 to the negative 6 molar, and then multiply it times the concentration for O3. And overall, what you end up getting is 2.2 times 10 to the 7th, and then the units are a little flipped, so liters over mole times second. I know I wrote this kind of weird, but this would be the answer for our K. So we got our constant. So remember I mentioned that this has to be experimentally determined, and in this exact way. This is the data, determine it experimentally, and then you go back and you calculate it.